Well, hi guys. We are going to take a look at a statement about how useful a power series is. And when this is going to be called an interval of convergence. And the questions are also asked with the radius of convergence. And this is simply a statement that will tell you whether or not you can use your power series for specific values of x. Now, I pulled this next theorem directly out of your book, so please do not write this down unless you just have to. This is theorem 9.20 out of your textbook, but I just want to talk you through this. There's only three possibilities for a power series when we're talking about interval convergence. One of those possibilities is that the series itself is so crazy that the only time it's useful is simply at its center, and you can't use any other values of x for it. The second thing that's possible is that there's some interval for which it will converge, and outside of that interval it diverges. So that might be something like you can only use it on the interval from, say, like -1 is less than or equal to x is less than or equal to 1. Or it might look like -2 is less than or equal to x is less than 5. So I'll show you how to check these endpoints. So this is just saying there's a restricted interval for where you can use the power series. And the third one is that the series matches the function so well that the series converges to the function no matter what value of x we're dealing with. So anyway, this is in your book, and I want to go show you in your book. This is on, well, page, whatever page it is. It's on the PDF file. I think this is page like where is it? Page 682, I think it was. Anyway, so these are some power series we've been working with. Let's take a e to the x sine and cosine. You see over here, the interval of convergence for e to the x sine and cosine is all real numbers. This means you can plug any value for x you want in here, and your power series will converge to that value of your function. For example, if you wanted to know e to the 50th, you could just plug in 50 to all of these x's all the way out to infinity, and it'd be exactly equal to that. So what we're saying with an interval of convergence is how good is the power series. Now with natural log, you can tell there's a restricted interval here. You can't use it outside of this interval. You can't use it at 0, but you can at 2. So let's go take a look at some of those examples. Let's just prove this e to the x one, x to the n over n factorial. Alright, so let's head to this next page, and let's just try this. So the question would be, find the interval of convergence for the power series for e to the x. Now, to do an interval of convergence, we are always going to use the ratio test. And the series for e to the x looks like this. X to the n over n factorial. So what we're going to do is we're going to set up the ratio test. Always use ratio test for interval of convergence. Always, always, always. So we're going to say the limit as n approaches infinity of, don't forget your absolute values, a sub n plus 1 divided by a sub n. I'll go ahead and multiply that by the reciprocal. Now for this to converge, the ratio test says that this value must be less than 1. So let's clean this up. My n factorial over n plus 1 factorial gives me an n plus 1 on the bottom. My x to the n plus 1 divided by x to the n gives me an x to the first in top, because there's one more factor of x in the top than there is in the bottom. Alright, now we're taking this limit as n goes to infinity, regardless of x. So if we're just looking at our n's, this is a bottom-heavy function, because don't look at your x. This is just as n goes to infinity. As n goes to infinity, this equals 0, because you're going to have x divided by infinity, and that is always less than 1, which means that no matter what x is, this will converge. And that's how you can get a series that acts so nicely that your interval of convergence is all numbers. Alright, let's go take a look at one that's just a crazy series that we just made up. Okay, it's not necessarily to the function that we know of. So I've got here, we want the radius and interval of convergence of this power series. So that's definitely going to start with the ratio test. So we're going to set up the limit as n approaches infinity of a sub n plus 1. So I'm going to go ahead and replace all of my n's with n plus 1. Okay, don't forget your absolute values, Mr. G. All right, times, and then I'll go ahead and multiply by the reciprocal. And then let's see, this has to be less than 1. So let's clean this up. Let's first of all deal with our exponentials here. 4 to the n plus 1 and 4 to the n. That just leaves me a 4 in the bottom. What about your x's? We've got just an x on top because there's one more factor of x on top. Then let's take a look at our n's. Okay, and then on the bottom I've got an n plus 1 squared plus 1 times n. Okay, so I sort of separated everything there. Now let's take a look at the top here. As n goes to infinity, if I multiply the numerator out, I'm going to get an n cubed. And if I multiply the denominator out, I'm also going to get an n cubed. And it's going to be a 1n cubed over 1n cubed. So the limit as n goes to infinity is the ratio of those coefficients because they have the powers are equal. So that means that I've got x over 4 times 1. And I need this to be less than 1. Here, I didn't get my limit to go to 0, so this is not going to have an interval of convergence of all numbers. I now have this restricted range. And so if I multiply both sides by 4, I get the absolute value of x has to be less than 4. This is called my radius of convergence. This means we are only going to be able to go left and right 4 from the center. So we can use this power series for the numbers between -4 and 4. But we're going to take a look at the endpoints to see if we can use those as well. So we're going to turn this radius of convergence into an interval of convergence statement. Absolute value of x is less than 4 means -4 has to be less than x has to be less than 4. Now we have to check our endpoints. I want to see if I can use -4 or if I can use 4. Like in that natural log interval of convergence, it went from 0 to 2. You couldn't use 0, but you could use 2. So let's take a look at how you check your endpoints. What I'm going to do is I'm going to try -4. So I'm going to plug -4 in for x and see what kind of series I have. So that's going to be from 1 to infinity of n times -4 to the n power over 4 to the n over n squared plus 1. Now this is the same thing as n times -1 to the n times 4 to the n. And then I've got the bottom 4 to the n times n squared plus 1. Now I can cancel my 4 to the n's, and I just have to take a look at the series. What do I have left over? I have an alternating series. So if it's alternating, I just need to check two things. We need to check and see what's the limit as n goes to infinity. Well, that would be n over n squared. That's bottom heavy, so that's 0. And are the terms decreasing? And they are, because the bottom is getting small. The fraction's getting smaller because the denominator is getting bigger. So we are decreasing, and so this is an alternating series that converges. So since this series converges at -4, I can use the -4 endpoint. Now let's check 4. If I plug in 4 for x, make sure I got it up here, n times, 4 to the n, over 4 to the n times n squared plus 1. My 4 to the n's would cancel, and I would get a series that's not alternating. And I'm going to have to use those tests we learned the first part of this chapter. I would basically compare this to the divergent harmonic series 1 over n, because I cancel out that plus 1, it's basically 1 over n. And since this diverges, this also diverges, which means I cannot use my right endpoint of 4. So my final answer for the interval of convergence is -4 is less than or equal to x is less than 4. Okay, that's how you use the ratio test to find interval of convergence and radius of convergence, and I will see you guys tomorrow.